Now, let us look at how the kernel deals with the system call, the mechanism. The system call function basically checks the validity of the given system call number. This is like the first thing that we have always emphasized, is that you want to make sure that the system call is legit and that it's allowed. Then you compare it to the number of system calls, basically checking the unistd.h, looking for the system call in the system call table. If the number of the system call is larger than or equal to the nr syscalls, if basically that system call does not exist, okay, then you basically exit with an error and you throw an error number, the negative inosys basically. Then otherwise the specified system call is invoked by basically fetching it from the table, and each element in the system call table is 64 bits, so it's 8 bytes. The kernel multiplies the given system call number by 4 to arrive at its location in the system call table. This is actually for 64-bit processors. So basically, first you check that the number of the system call is valid. Then you fetch the system call from the table, and then the kernel basically jumps to the system call using that mechanism that I just said, multiplying the given system call number by 4 to arrive at its location, the system call table, where it actually exists on memory. And the implementation has nothing to do with the mechanism. Some rules of thumb: you do not want to multiplex system calls. This is a bad idea. You want your system call to be clean and simple, with the cleanest and simplest interface, with the smallest number of arguments possible. You basically design an interface with an eye towards the future, because people will be using your system call forever. You design a system call to be as general as possible. You do not want a system call, you want something like the open and close system calls, which allows you to access I/O and allows you to access the file system, and allows you to access different things. You do not want very specific system calls that are useful for a very narrow scenario. You should not make assumptions about what architecture you're running on if you want your system call to be actually generic and run on different architectures. And you should provide mechanisms, not policies. So your system call should be a mechanism to do something rather than a solution. This is basically some design principles in general. Since the system call runs in kernel space, and we have said multiple times that we want as much separation as possible between the kernel space and the user space, there are mechanisms to write to user space from the kernel space, and there are mechanisms to read from user space into the kernel space. So to write to the user space, there is a function that is defined in the kernel that is called copy to user. And copy to user basically copies whatever. So you want now to return from the system call, for example. To return from the system call, you do not really return as a normal programming language. But, well, when you return, you find the return value right away. But what happens is that since you want this separation, you basically copy to the user memory. So you have your internal memory right now, and you want to copy. You've done basically some calculations. You have basically got like the get PID, for example, system call. Now you have the PID for the process, and you want to return it. You want to return it to the user. One way would be basically to directly interact with the user, which basically is a security risk. The other way is that while you are in the kernel space, or in the kernel mode, you basically copy the output of your syscall into the user memory. because the kernel memory is separate from the user memory. So you copy the output from the user space into the kernel memory so that when the user comes back in the user mode, basically it does not interact with the kernel, it just finds the value there magically. So this is the copy to user function. For reading from user space, you have a copy from user function, which is basically, well, we do not trust the user to pass us arguments. We will basically copy from user space, we'll copy from the user memory whatever data the user is providing. Both of these functions will return the number of bytes they failed to copy on error. On success, they return 0 basically, because they have succeeded and thus all data has been sent. So this is a syscall define 3, basically a system call taking 3 arguments, and we call it silly copy. And it has 3, since it's syscall define 3, so it has 3 arguments. So the first argument is a pointer to source, the second argument is a pointer to destination, and the third item is a number of the type long called len. And then you'll basically copy from user, okay, the data that the arguments that he has provided to the kernel, okay. So to get the arguments, you copy from user the source and the len, okay, and you copy them into a buffer. The buffer is basically a memory address that is in the kernel, that is in the kernel memory basically. And then since this is a silly copy, then what it will do then is that it will copy to the user in the destination DST whatever is in the buffer and the len. Okay, so it basically literally does nothing. It just takes input from the user and copies the input from the user into the kernel space, and then copies the same input from the kernel space into the user space. So it does nothing basically, and then it returns the len. So this is a very, very dumb system call. To check if the caller is allowed to perform an action, for example, so you want basically to make sure that, well, he is allowed to send me these values, he's allowed to send me arguments, he's allowed to touch this part of memory. There is a function that is called capable. So this is an example where capable is called to check if the user is allowed to change the niceness value of other processes. Nice values is a way to basically give priorities in the scheduler. So you basically use nice as a way to enable better scheduling basically. So you have multiple applications running, you have multiple processes running, and you would like some of them to run faster than the others or to take more CPU time than the other. So if you change the niceness values of these processes, you can actually get them to run faster or slower. And capable, basically cap sysnice, is basically a way for the kernel to check if the user calls the syscall to change the niceness values of another process, because a user can change the niceness value of his own process, basically saying that, well, I am willing to release resources for others. I'm being nice basically to others. But if the user tries to change the niceness value of the other processes, then the kernel will check it using capable. There's at default, super user in Linux possesses all capabilities and non-root possesses none. So there's this concept of different user privileges in Linux in general. There's super user or sudo, who's someone who, he's a super user. He can do whatever. He's typically your system administrator or someone who owns the computer. So if it's your own computer, you are probably your own super user. and you possess all capabilities. You can basically destroy your system very easily. A non-root user, on the other hand, cannot, for example, access kernel files on the operating system. So something as benign as seeing the files in some of the folders, he will be stopped from doing that because, well, you're not allowed to do it. You're a non-root user. Capabilities flags are set for different users are set in include /uapi /linux /capability.h. This is where actually super users and non-super users are defined. So finally, almost done here. This is basically the reboot.c. This is a system call that is, well, the reboot system call. You probably know what the reboot system call does. And this is to reboot the system. And you see, I mean, many of the system calls, you'll find a very detailed commentary from the programmers or from the developers who developed this system call that you can basically, that can guide you to what this system call actually does. So reboot.c, it has the syscall define reboot, which takes four numbers, four inputs as input. So what do I do to implement a new system call? There is a guide for a generic system call implementation in the Linux documentation. You'll find it on the folder, documentation, docs basically, and you'll find it online on this link. And this can be your start point for actually getting your system call implemented. So how do you test a system call? Suppose you just added a foo syscall to your system. You place a macro on top of the program is all it takes to get your stuff up and running basically. So hash define and underscore number underscore foo 283, and this is a syscall that takes 0 inputs and yeah, and it returns long, and it's called foo. This will basically test your system call for you, and this is your this will define your system call, and this will test your system call. You have basically C code where you have int main and long stack size equals foo. This is basically you importing your syscall, and this is you testing your syscall. So with this, we're done for today. Thank you, and let me know if you need help with the project.